With that, we can continue to autoencoders for recommender systems. And you're going to see its relationship to collaborative filtering. What is collaborative filtering? The idea is that you want the representations of your users and the items to collaborate. So that's the idea. You want to see how similar they are to each other. And this one is going to be more clear as I show you the math. And you have two competing methods. One of them is matrix factorization. The other one is neighborhood models, like k nearest neighbor. We are not going to do neighborhood models, but matrix factorization, I'm going to explain a little bit. And then you're going to do rating-based collaborative filtering. What is that? Here, unlike session-based, you know the ID of your users. Perhaps you are not keeping their essential data, such as their name, social security, you name it, but you keep their ID. Perhaps you know their user ID, like similar to somebody knowing your student ID. This was different from session-based when you didn't even know the user ID. You could know it, and if you know it, then that's more information that you can leverage, and we are going to see how. But let's assume you don't have it. For session-based, you assume you don't have it. Here, you assume you have the IDs. The other one is you have n items. So n users, n items. And for each user, you want to recommend an item. You're going to collect some data. Your users are going to interact with your items, perhaps on your website, and perhaps they are associating ratings to them. They don't even need to associate ratings or star ratings. The fact that they clicked on an item, you can think of that as a rating, click versus no click. Or if you have more information like the ratings, that's even better. Each user, let's denote it by U. Each item, let's denote it by I. You have n users, n items. And let's look at this. If you pick a user in your data set, you can check, did this user interact with the first item? Did they interact with the second item? Did they associate a star to it? Did they click on it? Did they interact with the nth item? And that's going to give you a vector. It's a sparse vector. Most of the times it is zeros, and sometimes it is non-zero. The zeros, you cannot interpret them as the user didn't like that item. Perhaps they never encounter that item. Perhaps they're not aware of that item. They're not aware of that particular movie. So you cannot interpret them as dislike. And the ones that they click on, you cannot interpret them as like. But if they associate stars, then you can start interpreting them. The positive ones, if somebody associated more stars to a particular item, then you can say they liked it more. You can have a similar story for your items. If you pick an item, you can ask, did user 1 rate this item? Did user M rate this item? That's going to give you a vector. This is m-dimensional, the other one is n-dimensional. And then you can do item-based AutoRec. What is that? Like any other autoencoder, you take one of these vectors, and because this is item-based, you are picking this vector. You also have the option to pick user-based. But let's pick item-based. This is a vector. You push it through a neural network, and then you're asking the neural network to reconstruct the same vector while putting some regularization terms on the weights. And so what is W? This is the last layer. Your neural network is a very simple one. It's fully connected. Matrix vector multiplication, nonlinearity times the matrix, add the bias, and then you want these matrices to be penalized if they get too big. You want them to be around 0. And the only catch is this O here. You're writing this loss function, this reconstruction, only on the non-zero elements here, where you actually had data, because the 0 ones you cannot interpret as this user didn't like it or liked it. You have no information there, so you don't include that in your loss function. So what does it mean exactly? How do you do that? If you take this vector, push it through your neural network, you can pick a particular user that interacted with that item and include that in your loss. Otherwise, you don't include it. You can do a similar thing with user-based. Okay? So far, so good. It's in terms of visually speaking, this is exactly what is happening. You have the vector for your item. The output is the same as the input, so it's autoencoder. And now you're trying to reconstruct. And these ones are the biases. Let's see some results. Movie lens, I want you to explore. Another metric is root mean squared error, which is very standard metric whenever you're doing regression. And item-based is doing a little bit better than user-based. The lower is better here. You can do systematic studies. What should be my F? What should be my G? So G being sigmoid, F being identity. So no activation function here is doing the best. Netflix, movie, lens. Then you can compare to the state of the art prior to this work. And then as you increase, then this is not the training process. This is actually the number of hidden units, the width of your neural network. The higher the width, the lower is going to be your root mean squared error, the higher is your performance. So was AutoRec clear? Okay, perfect.